Let's look at number 15 on the Newton's Laws worksheet. In number 15, you're going to realize that there isn't only one mass. There's actually a system of masses. So when that's the case, how do we tackle the situation? How do we calculate the net force acting? How do we calculate the acceleration? And how do we calculate the tension on this ropes? So our goal is to find how these masses are accelerating. So looking at this picture, we have three masses. There's a 2 kilogram here, there's a 3 kilogram here, and a 5 kilogram mass sitting on the table. These are hanging. So we're going to analyze the motion of each one of them. And to do that, first we need to isolate each one of these masses and see each of them in their own bubbles. So I'll do the same for the 5. That will be the bubble for the 5. Now, to be able to analyze the relationship between the masses, we are going to also need to see that how we identify tension. What you need to know is that unless the rope is changing, the tension will be the same. So tension is the force on a rope. And everywhere on this one rope will be the same tension acting on all of the masses that it is connected to. Since it is connected to this 2 kilogram mass, pulling it upward, we are going to show it upward on the 2 kilogram mass. But it's not alone, it's also attached to the 5 kilogram mass, so I'm also going to show it on the free body diagram of the 5 kilogram as such, because this force acts on both. Let's look at the other rope. Since this is all one piece of rope which is connected to two masses, sorry, I'm gonna fix that. That is one rope, and the tension on that rope is labeled T2. On the 3 kilogram, on the point that is attached, it is pulling this object upward, so there is T2 on the 3 kilogram. But this rope is also connected to the 5 Newton and it's acting towards the right. So in that direction, on the 5 kilogram will be a T2. So what I have done so far is show the force of the rope acting on the masses. On the diagram, let's add all the weights, because that's also, well, obviously always going to be the force that acts on every mass. So, and mass is always drawn downward on the page, which you already told me last lesson. So for the 2 kilogram, we learned that weight equals mass times the gravitational acceleration, where gravitational acceleration is 9.81. For simplicity of solution of this question, let's not worry about 9.81 and let's round it off to 10. So for this question only, let's just take gravitational acceleration to be 10 newtons per kilogram. Okay, at this point I'm going to pause and guess that you're going like, what? Acceleration is meters per second squared. Why is she suddenly using a different unit, Newton per kilogram? Well, guess what? Force is mass times acceleration. Force is in newtons. Mass is in kilograms. Which means acceleration will be Newton divided by kilograms, because acceleration is force divided by mass. So Newton per kilogram will be equivalent to meters per second square. See, this is the unit for acceleration. If you divide both sides by kilogram, you will see that these units are actually equivalent just because of Newton's second law. So that was me sidetracking a little bit. Getting back to the question, if the mass is 2 and gravitational acceleration 10, you probably see already that this can be a 20 Newton force acting downward. Likewise, 3 times gravitational acceleration, 3 times 10, the weight of this mass is going to be 30 newtons downward. Let's do the same on the 5 kilograms. This is going to be a 50 Newton downward. Well, this one is acting on a surface and it's not going through the surface. So there must be a reaction force which has to be equal to 50 newtons upward. So these are balanced. This mass is vertically balanced, but we don't know about T1 and T2. So there is no friction, and these masses are not resting against the wall, so there is no friction or normal force to show on either of these masses. And this one, we don't have a friction to show because the question does tell us that it's a frictionless surface. So we've basically answered part A. We did part of part A, draw a free body diagram. I did that on the picture. So the first thing I did was to draw a free body diagram for each mass. I can do this on a bubble or separately. That's the first step in examining motion. The next step is going to be the net force. So what are the forces acting on this system? Let's see which direction this system can move. This system can move in two directions. It can move in this direction, or it can move in that direction. Which one is it going to be? So this mass is either moving up and down, this one is either going right or left, and this one is again moving up and down. They're all related. So you just have to find along that line of motion, and I'm calling it line of motion because they're not all in the same dimension, but it kind of is the same direction if they're all moving this down, this to the right, and this one up. That's either clockwise or counterclockwise. So how do we know whether this system is gonna go clockwise or counterclockwise? The answer is in the net force. So what are the forces acting on this system along the line of motion? Well, we have the 20 Newton pulling down, and we have the 30 Newton pulling to the right. We have the tension, but this tension and this tension as a system would cancel because it's in two directions if you look at the whole thing. Again, for T1, as part of the whole system, T1 is acting clockwise and also counterclockwise. So tension on a rope is not going to impact a whole system movement, but it will be important within the motion of each mass, which I will explain in a minute. There's also this weight and the reaction force. But what did we say about finding net force? We are looking for the forces that are acting along where this system can move. 50 Newton is vertical, just like any weight, but that is not a direction this mass can move. This is not going down. It can only go to the right and left. So along the line of motion, which could be clockwise or counterclockwise, there's only T1 and T2. 50 balances the reaction and it pushes against the table, and since we don't have friction, it's kind of irrelevant for us just yet until we discuss friction. So I can ignore that in the equation. So we're left with a 30 that's pulling clockwise and a 20 pulling against it. The minute you see that, you write 30 minus 20, and that is 10 Newton as the net force on the whole system. So that answers part A, which takes us to part B. Now we're looking for the acceleration of the system. So I'm going to do F net. So this is the solution of part B over here. F net on the whole system. Okay. This is equal to 10 newtons. And it's going to be equal to mass of the whole system times the acceleration of the whole system. Now, what is the mass of the whole system? We have masses. They exist. They are there. There's a 2 kilograms here, a 5 kilogram that is moving together with the other 2, and a 3. So we have a total of 2 plus 5 plus 3 kilograms of masses, which makes a 10. So we find that the acceleration is 10 divided by 10, which is 1 meters per second square. So now that we know these masses have a common acceleration because they're all connected, an acceleration of 1 meter per second square, this applies to every mass in the system. But we have to be very careful about the direction. So let's go for that, because to find the tension, I am going to use F net equals ma, not for the system, but for individual masses this time. And to do that, I'm going to need the acceleration. So let's do part C over here. Now, since we're looking at T1 is acting on 2 of the masses. It's acting on this 2 kilograms, so I can solve looking at this bubble. It also acts on the 5 kilograms, so I can look at that bubble. I want to choose the easier one, so I'm going to go with this, because this mass is going to have the T2 involved, which I don't really know. So let's avoid what we don't know. Let's look at the simpler version. I have an upward force of T1 and a downward force of 20 acting on the 2 kilograms. So I'm going to use F equals ma, F net equals mass times acceleration. See, I'm using the same innocent, funny little formula, which is not very innocent at all. So we want to find the F net, but this is only for the 2 kilogram mass. So I'm applying the same formula, which is Newton's second law, only for the 2 kilogram mass. So I'm obviously looking at the 2 kilogram mass only. I now know its acceleration. This applies for every mass in the system, so I'm going to put the 1 for the acceleration. Brilliant! I've the right side sorted. What is F net? Now, to write F net, I will obviously write T1 over minus 20 or 20 minus T1. Which one is it going to be? I need the bigger one. Which one is the winner? To find the winner, I need to know which way this acceleration is. So go back to the whole system. Is the system sliding clockwise or counterclockwise? Well, if this is bigger, it should obviously be sliding towards the right. So that means the acceleration of the 2 kilogram should be upward. Well, for the record, let's add it on the free body diagram of the 5 kilogram. Acceleration will be to the right on this one, and it will be downward on this one. I'm not adding it as a force diagram because the force diagram only shows forces. I'm just writing it on the side to know which direction force is bigger. So if I look at the 2 kilogram, if this is accelerating upward, answer this question. There are 2 forces. There's T1 upward and 20 downward. Which one is winning? Which one must be larger in size to cause an upward acceleration? The one that is acting upward. So T1 must be bigger than 20. So I'm going to write F net as the winner minus the loser. And there's my equation. So then I solve T1 equals 2 plus 20, which is 22 newtons. That's my T1. Okay. While we're at it, we could solve for T2. Well, actually, that's the next part. So let's do that. Let's do T2. Let's draw a line so we don't get them mixed up. Let's solve for T2. Now for T2, I'm going to look at this mass because it's what it's acting on. Now I know the acceleration, it's 1. This applies to all of the masses because it's a system, they move together. They accelerate, they have the same acceleration. And so I know this is a 1. So I'm now going to use the 3 kilogram mass. Okay, this is the one I'm looking at. And I'm going to use F net equals mass times acceleration. So I know mass is 3. I know acceleration is 1. And here I'm supposed to write the net force. And there are 2 forces that I see in the free body diagram. This accelerates downward because it's sliding downwards because the 30 is winning against the 20. So among these two acting on the 3 kilogram alone, 30 or T2, which one is winning? If it's accelerating downward, the downward force must be winning. So I'm going to write winner minus the loser. And there is my equation for T2. And when I solve the equation for T2, I'm going to move T2 to one side and everything else to the other side. That is 30 minus a 3, which gives me 27 newtons. That ends the question. That's all it's asking. But I want to do a check. So what I'm going to do, we found T2 to be 27. And we found T1 to be 22. If I was right to assume that T1 is the same acting towards the left on the 5 and T2 is the same T2 acting towards the right on the 5, this equation should check for the 5 kilogram as well. So that's what I'm going to check now. I'm going to write F net equals mass times acceleration equation for the 5 kilogram. Now, and see if it checks out. Well, if T1 is to the left 20, T2 is to the right 27. Which one is larger? Which one is winning? Obviously 27 should be winning, so I'm going to write winner minus the loser. This gives the F net on the 5 kilogram equals its mass times the acceleration like everybody else. Oh, big surprise, 5 equals 5. Wow, the equation checks out. Surprise, surprise, everything checks out. It all makes sense. This was just for extra practice. This was just for the sake of showing you that I wasn't making any of this up. And that's it for this question, how we approach system questions. So now what you should do is to copy this down, okay, and make your own drawings, but don't copy the solutions directly. Have this on your screen, but on your workbook, try to solve all of this from scratch, because you did the first step, you listened to me teaching it and solving it. The next step is you trying it on your own. So now go ahead and try to solve the same problem from scratch on your own. Just answer the questions, find the net force, draw a free body diagram, and calculate acceleration of system T1 and T2, and see if you get through by getting the same answers. And that's it for this question. Thank you.